We're back. So the last review session we had, the last video review, there was a question posed at the beginning. Why does Waikiki Beach warm up faster in the daytime than the water does? And you can see the picture there. Beach is warming faster and the ocean's warming more slowly. And the answer to that question has to do with a new topic for you guys, and it's been staring you on the front of the reference tables the entire year, and that's called specific heat. And sand and water have very different specific heats. So specific heat is simply the amount of heat required to raise a given mass of a substance 1 degree Celsius. Now this is a related topic. Remember that heat is energy transferred from a higher concentration, which we call source, to a lower concentration called a sink. And we're going to measure heat energy in this unit, in units called joules. We used to use calories. Now we're using joules. And 1 calorie is about 4.184 joules. And what that means is it takes about 4.184 joules of energy to raise 1 gram of water 1 degree Celsius. So calories and joules are both forms of energy. And you can see this diagram on the left shows a bomb calorimeter. This is what they use to actually measure the energy values of certain foods. I can remember doing this actually in chemistry lab a long time ago. And here are some common specific heats. We got water in its 3 phases: dry air, basalt, granite, iron, copper, and lead. And note that the reference tables doesn't use calories anymore. So if you're digging out on old reference tables from a stack trying to solve a question and these numbers are in calories per gram, then you need to toss that. And here's what your reference tables chart looks like. This is the same exact set of numbers. This is on the front cover of your reference tables. Okay, related topic, the heat of fusion. Heat energy gained or lost. Now this happens when you gain heat or release heat when either melting or freezing a substance. And for water, the number in your reference tables is 334 joules for every gram of water either gained to melt or released to freeze. And this chart is also located on the front cover of your reference tables, right near the other chart that we just discussed. And the heat of fusion has to do with this area right there. So you can add 334 joules per gram to melt, because you got to add heat to melt, but remove 334 joules for every gram to freeze that water. And note that the temperature remains the same until the phase change completes. It reaches a standstill until all the ice melts or all the water freezes, and then temperature can either go up or down. Okay, the heat of vaporization. This is the heat energy gained or lost when vaporizing or condensing a substance. So now we're dealing with turning water to steam or water vapor and water vapor back to liquid water. And for this process, it's a lot more energy, either gained or lost. 2,260 joules for every gram of water. And that is represented on this graph by a longer horizontal line right there. And that flat line represents the amount of heat gained or lost. 2,260 joules for every gram. And once again, the temperature stays the same. It reaches a roadblock until every single gram of liquid water has vaporized, or if you're going backwards and condensing, every single gram of water vapor has cooled down enough to condense into liquid. Then the temperature can go back down even farther. Okay, during change of state, energy is converted to potential energy or stored heat, and this doesn't show a change in temperature. This is why the line stays the same for any phase change. And it also mentions up there that condensation and freezing must release heat, and that's these two things. Must give up heat to go this direction, So there's our remove heat. And melting and evaporation must gain heat energy. So melting and evaporating are phase changes that require the addition of heat to go from left to right. And that's what this arrow shows. So it just depends on which way you're going. You either got to remove heat to go left or add heat to go right. And nature does this every day. Okay, we're going to be working on some heat problems coming up in a few minutes. And just to go over some basics here, you can see Q represents heat, not H. M is going to be our mass. Little c is going to be our specific heat. And that's measured over here in this chart. Temperature is obvious. Heat of fusion and heat of vaporization are these numbers up here. The fusions are the first two and the vaporizations are the second two. And there's three equations to be used today, and one of them involves a temperature change, changing temperature, and Q is heat equals the mass times the specific heat times the temperature change. And you use this whenever the problem requires you to either heat something up or cool it down, and there it shows a temperature change. Now when you're changing phase, remember the line there is a horizontal line. There's no temperature change until the phase change is complete. And so because of that, the formula doesn't have any delta T in it, any temperature change. So it's just the mass times the HF or the mass times the HV, which are those, once again, those numbers HF and HV. All right. Here's our first problem. This is a 5-stepper, so we're going right to the difficult one first. How much heat is necessary to change 10 grams of ice at -20 Celsius to water vapor at 150 Celsius? And this is going to be our -20 over here. And our 150 is going to be its final highest temperature over there. And so we're going to stop the video here. We'll come back in a different one, and we're going to solve this problem.